school physics, South Shore High School, class of '64. Had a horrible teacher named Oscar Lamondres. Oh man, called him Mumbleson. I know my physics. I couldn't speak well, but he had a couple of really cute experiments. And this one I love. I should try it. If I ever find the right components, I'm going to put one of these together. And it's just this simple. And let's just add a couple of things to it. A couple switches. Oops. All right. If the switch is closed, you know, the current will go around the inductor L or the capacitor C, and it's as if they're not in circuit. So what are you going to have? You have 120 volts AC, just going to get it coming out of the socket here, and it will light this light bulb to full brightness. Nothing magic about that. Now, if I were to open the switch and let the inductor be in series, meaning current has to flow through the inductor to get to the light bulb. Series means end to end. These guys are in series. Parallel means they're side by side. In this case. And I know Greg went through the equations for how to calculate series and parallel impedances. What I'm going to do is throw a little extra detail in there that you need to know. Or two. So in series, the current that flows into this guy has to flow out of that guy, and what flows out of that guy has to flow into this guy and out of that guy. Okay, so that's the whole idea of series. The current has no place to go but through each component. If you're in parallel, it can go through this, and it can go through this, and go through this at different rates because maybe these are higher impedance, higher resistance values than this one, and the current tends to be pushed into the lowest resistance path. You have the least resistance, more current flow. Makes sense? So what do you expect is going to happen? The light bulb's going to get dimmer because some of that voltage is going to drop across this guy, and some of it's going to drop across this guy. And one thing I'm going to teach you a little later tonight is whatever voltage you have here has got to equal this voltage and this voltage. Every voltage that goes up has to go down somewhere. All the voltages in a loop will add up to 0. So if you have 120 volts here, some of it will drop here, whatever doesn't drop here will drop there. But they drop across this impedance and the drop across this impedance will add to 120. You cannot accumulate voltages in a loop. That's one of the two Kirchhoff's laws. It's the voltage loop law. The other one is the current law, which says whatever current flows into a junction has to flow out of that junction. If there's 3 resistors connected together, one flows in to a node, and the other 2 flow out. This I in has to equal this got to be a 1. This out 1 and out 2 have to equal the whatever current flows in here has to flow out there. You cannot accumulate any current in the node. That's Kirchhoff's. Spelled almost the same way as the exit on Route 53, Kirchhoff. Kirchhoff's law for nodes, current node law, is that all those currents into the node have to equal 0. When I say into the node equals 0, what's flowing out is a negative into. So this is a negative into, this is a negative into, this is a positive into. Add them all together, they're 0. Whatever flows in, flows out. That's why we have signs and conventions for voltage flowing from positive to negative, so that we can do this a little bit of mathematics. All right, so guess what? Not surprisingly, the bulb glows less dimly, or less brightly. Now, the switch gets opened up again, and this switch gets closed. Now the current, or the other way around actually, this one gets closed and this one gets opened up. So now the current is flowing to the bulb and the capacitor. And what do you get? Same thing. Some voltage drops across the bulb, some voltage drops across the capacitor. Because it's alternating current, the current can flow through the capacitor. It's obviously can flow through the inductor. The inductor will impede it by having this magnetic field expand and contract and producing a back EMF, a Lenz's law type of reaction. And the capacitor will conduct because the charge is one way, the current flows the opposite direction, discharges and charges the opposite direction, but while it's charging, it's basically letting current flow into one set of plates and out the other, and vice versa, so it's like it's flowing through it. You get impedance here, you get impedance here, this thing gets less bright. Common sense, nothing unusual here. Now open both sets of switches, and this, and this, and this are all in circuit together. And the bulb gets even dimmer. Now you got voltage dropping across this guy, and this guy, and this guy, and the bulb's barely able to be seen because it's really dim. What's the point of this, I wonder? If I draw an arrow through this inductor, it means it's a variable inductor. If I drew it through a capacitor like this, you'll see that on your schematic list, I think. It's a variable capacitor, meaning there's some way you can actually change the amount of inductance or the amount of capacitance. In the case of a capacitor, you usually have two sets of plates that slide between each other, in and out, sort of. If you ever look inside an old radio, as you turn the tuning dial, this round set of plates and this other round set of plates slide next to each other and away from each other, so basically you can vary the amount of capacitance by the amount of metal that's facing an opposing set of metal with some airspace in between. How do you make an inductor variable? With a metal slug that can be moved in and out of the coil. Literally, you put this rod in the core of the coil. Why does that work? Because if it's the soft kind of metal, the magnetic field flows through the metal more easily than it does through air. And in doing so, the magnetic field doesn't spread out as much. It tends to stay concentrated in the middle of the coil, in that slug, where the metal is. So as you put more metal into the coil, the inductance goes up because the magnetic field gets concentrated where the wiring is. It doesn't spread out as much. So you can find in old radios what's called a slug-tuned coil, where a metal slug is with a screwdriver, a screw shaft, driven down into the coil, and when you turn it the other way, you turn the screw the other way, the slug comes back out. And in doing so, you change the inductance. So the instructor had a slug that he dropped into the coil. And at some point, the bulb went to full brilliance. What? This thing's supposed to be impeding, and this thing's supposed to be impeding, and this thing is supposed to be the load which gets the result. And yet, I got an inductor here, I got a capacitor here, and it's as if neither one's there, the bulb's at full brilliance. So what does that obviously mean? This guy and this guy not only have perfectly opposite characteristics, they can cancel each other out. The inductance here and the capacitance here offset each other. Now that's cute. What it means is there's one thing on that. It's athletic. I tend to drop things a lot. All right, so here's a frequency line, and with the capacitor, as you go up in frequency, the current goes up. And with the inductor, as you go up in frequency, the current goes down. Oops, that's actually current, but this is the I sub L, and this is the I sub C. meaning the current through the inductor L or the current through the capacitor C. So as you go up in frequency, capacitor's more capable of carrying current. And as you go up in frequency, the inductor is less capable. Where do they cross? You have a situation where the amount of capacitive impedance and the amount of inductive impedance are equal and opposite and offsetting. That point has a name, and it's called resonance, or the resonant frequency. That is when you are tuning for a radio station. What you're trying to accomplish is you are trying to get the capacitor and the inductor at the particular frequency of interest to cancel each other out. If it's a series network like this one is. If it's a parallel one, it has the opposite effect. The current will go through the capacitor when you're too high, it'll go through the inductor when you're too low, and if they're just right, they'll go through neither, and you'll get maximum voltage dropping across that network. Let me draw a picture of that. As I said, when you're at lower frequencies, the current wants to go that way. When you're higher frequencies, the current wants to go that way. That's the path of least resistance. When you're just the right frequency, you can't go either way. And basically, you're going to get a voltage at that frequency. And that voltage at that frequency, you take it, you put it through an amplifier, and do all kinds of cute things, is the tuning of the radio station you want to listen to. This is what makes radio work, folks. The time varying features of an inductor and a capacitor. One conducts better at high frequencies, one conducts better at low frequencies, equal and opposite characteristics. Put them together, you have a tuned circuit, and they work at one frequency called the resonant frequency. And that's how we select our stations. Very nice feature. Now let's go back to those equations that Greg was talking about last week. He said the reactive impedance of an inductor, he just wrote JWL. I'm not going to use that terminology yet. We'll get to it where I'll explain what these things are. What is more in the English language that you'll understand is 2 pi FL. Omega is 2 pi. And, excuse me, 2 pi times the frequency of interest. He said it's the radial frequency, it's the circular frequency. It's the number of radians per second, and a radian is a segment of the circumference of a circle that equals the radius. And remember what pi is? It's the circumference over the diameter. That's the circumference, that's the diameter. And half the diameter is called the radius. So if pi is c over d, it's also equal to c over 2 times r. So two radiuses are in the circumferences, and therefore 2 radians, or sorry, 2 pi. Let's just do this equation. We'll solve for c. C is equal to r times pi, 2 pi r. There are 2 pi radians in a circumference. So every time a generator rotates once, it's going through 2 pi radians. So therefore, the radian frequency is 2 pi times the cycles per second frequency. That's where that came from, just so you know. Not that you need to know it, but that's where it came from. Okay, and with the capacitor, it's 1 over j omega c, which is, in more plain English, 2 pi f times c. C being the capacitance in farads, L being the inductance, and what did Greg say last week? What was the measure of inductance? Begins with an H? Henrys. Henrys, very good. The reason for the J is a bookkeeping thing. The J says this is reactive. If it's resistive, it won't be there. So that when we have, as I said before, impedance, we'll have a resistive value and a reactive value. This just says that's the reactive value. So if I don't put an extra, but put a number, the J says the number next to it is really representing X, and the one without the J is representing R, and that's how we keep them apart. And because this happens to be an imaginary thing, and this is a real thing, together that's called a complex variable. There's a whole course on it in college. I'm sure none of us took it except me, but even if you did, I feel sorry. No, it was actually a fun course. It was really easy, but that's the purpose of it. And the reason we do that is so that we can have a kind of a graphical way of representing this thing. By convention, anything on the horizontal axis is R, anything on the vertical axis is X. If it happens to be inductive, it's positive, and if it's capacitive, it's negative. And when you talk about a resistor and a capacitor, it will have a value that's so much R and so much JX. And it's a point on a map like that. It's just like a bookkeeping system for keeping track of them.
1287, 1018 Willow Road, Buffalo Wild Wings, a fire alarm. Code 38, Tower 12, Rescue 12, Engine 11, Glenview.
Hot Wild Wings, come get them.
1287.
Yeah, I know that place. Isn't that right just north of the Glen?
Buffalo Wild Wings, a fire alarm.
I used to go to Sweet Tomatoes in that area too. I wonder if they're selling anything for cheap. Yeah, full of fire extinguisher stuff. All right. Yeah, this, by the way, this is the fun of ham radio, getting involved in public service. Never told me here. That's my work phone. Oh, it's my boss. Ooh. Tim, I'm teaching.